Water tanks provide a rich source of related rates problems, with the idea of flow and heights being associated through volume calculations. So we're going to imagine a conical water tank, so a cone-shaped water tank, with a top radius of 2 meters and a height of 4 meters. And it's going to be leaking water at a certain rate of 0.5 liters per second. So what I would get from this immediately is we're going to be talking about a volume change, and it'll be 0.5 liters per second. What we might wonder is plus or minus. Well, that depends on what volume we're looking at. Certainly 0.5 is going to be in there though. How fast is the height of the water in the tank changing? So we're going to be talking about the height of the water. The cone itself is 2 by 4, but the actual level of the water will be given by h of t. We'll actually call it h of t here to show that it's changing with time. When the remaining water in the tank is at a height of 2 meters. Okay, so when h is going to be going down, 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 and when it hits 2 meters, we're curious to know how quickly that height is changing. Would we be able to see it, or is it dropping down really quickly? What's the rate of height change there? Well, again, we have one rate. We want dH dt. How are these properties going to be related? Well, we have a cone and we have a height, and we have to remember something about volumes. So we might want to go for the volume of a cone. In this particular case, it'll be the volume of water in the cone up to height h. So that volume, which is changing with time, will be equal to, well, if we're only filled up to this height here, it'll be 1/3 pi, we better slide an extra variable in here. Let's call that r from here to here. So r of t, and that'll be squared, pi r squared times h. So the volume is changing with time, the radius will change with time. It'll be 2 at the top when the tank is full, and it'll be lower when the height of water is lower, and we also have the height itself changing. So this is a little more complicated than our last scenario, because we actually have 3 variables that are changing with time. Fortunately, 2 of these ones are much more closely related. In fact, we have a ratio from the cross-section here. The radius to the height will always be in the ratio 2 to 4. So what that lets us do is, I would say let's get rid of h here. Actually, no, we want dH dt. Let's get rid of r. So r could be written, and that's also 1/2 here. R could be written as 1/2 h. Does that make sense? When h is 4, the radius is 2, which is 1/2. Perfect. So we can replace our r's, or r of t, because it's changing with time, with 1/2 h. So we'll simply write it as v, r, and h now, though. We know they change with time. R is 1/2 h, all squared, times h. And so we get volume is 1, that'll be 1/4 times 3 is 1/12, pi h cubed. And again, this is something that's always true. That's the first objective in any related rates problem, is to get some equation, some relationship between the variables that you're interested in, volume and height, and how quickly they're changing. You get a relationship between them, and that relationship has to be true regardless of when you're looking. There will be a time where we bring in this 2 meters, but before we can differentiate, we need to have something that's true for all time. We'll go to the next page and see how we can do that. With this relationship in mind, what we're going to do next is what we did with implicit differentiation, remembering that we know dv dt and we want dH dt. So we're going to take this relationship that's always true and infer that how it changes with time must be the same on both sides as well. So we're going to get a dv dt, and over here we're going to have a pi over 12, 3h squared. The derivative is with respect to time, so it'll be dh dt here. And this is great. This is exactly what we want. Well, there's one that we needed to know. We needed to know dv dt, and let's actually take a step back for a second. We have that here, but it was a little unclear what this volume was. Now our volume is very clearly the volume of water in the tank. And so if water is leaking out of the tank, then dv dt must be negative. The volume is going down, so the rate of change of volume with respect to time, if volume is in the tank, this volume derivative must be negative. With that, we can start doing some calculations and actually hone in on dh dt. So dh dt, bring all this stuff to the other side. We'll have minus 0.5 times 12 over 3 pi h squared, and a half times that is 6. 6 over 3 is 1/2, and 1 over h squared. Perfect. This is the rate that we wanted. Here is a formula for it, and we are told we wanted at h equals 2 to calculate the rate. So dh dt at that particular instant will be 1 over 2 pi times 2 squared, or negative 1 over 8 pi. Meters cubed per second or liters per second? In fact, we should take a step back, think about that for a moment, and we'll check the problem. All the units we had here were in meters, but the units of dv dt were in liters per second. Okay. Remember the conversion factor from liters to cubic meters? There's 1,000 liters per cubic meter, because a liter is a cubic decimeter. And it takes 10 decimeters to equal 1 meter. And so if we have things cubed, we have to get 1,000 of them. So in fact, this negative 0.05 isn't right. If we're in meters, our units, this will be 3 zeros, then a 5, if all of our units here are meters cubed per second. So as long as we're careful about that, we're at our negative 0.5, there we go. So we're going to have 1 over 1,000, 1 over 1,000, and 1 over 1,000 here. Now, does that seem extreme? Well, think of the size of this tank. We're going to go back to the picture. At the point we're interested in, this tank is as high as a person, 2 meters roughly. It's also a meter across, so about the size of a person. And we're only losing water at half of a, half of a 1 liter milk jug per second. So it's not much volume that we're going to lose per second relative to the volume that we're at. So our height, how is our height going to change? It's going to be decreasing, so the negative sign's good, but it's going to be decreasing very slowly. And that's what's captured by all of these terms here. So this, in fact, would be our rate of change of the volume, of the height. This is how the height would be changing in meters per second as the tank is emptying. All right. One last concept follow-up. What if we ask the same question, what's the rate of the height changing, but if we looked up above 2 meters, what if it was up here at, say, 3 meters? Would the water height be changing, decreasing more quickly or more slowly than the value we just calculated? Think about that for a second, and there's 2 nice ways to go about that. All right. I think we can make 2 arguments that the height will be changing more slowly at 3 than at 2. The first reason is that there's more surface area here. We're talking about a wider range of water at the top. And so when we're losing our 0.5 liters per second, dropping that out the bottom is going to lead to a smaller decrease than when we have a larger area here. Or sorry, a smaller area here. Smaller area means each liter you lose will have more of an effect on the height. That's a qualitative answer. A more quantitative answer is to look here. dH/dt is given by this expression here, regardless of the height. If we use a larger height, we have a 1 over h squared term in here, we're going to get a smaller dH/dt. So if h is higher than 2, we're going to get a smaller dH/dt than if h was 2. And so both of those analyses lead to the same answer, that if we were to consider a higher watermark with the rate of volume change being kept the same, losing 0.5 liters per second, we would get a more slow drop in height here, faster, faster, and faster still when you get near the bottom, when the last thing just flushes out. The rate of change of height will actually be quite high down there.